We now continue with examples of linear equations. So let's try to do an example like this. Let's say we have 3y prime plus 15y is equal to let's say 6x. So this equation is linear. And so we should be able to solve it by using the integrating factor. So use the integrating factor. So remember that integrating factor mu of x is equal to e to the power integral of p of x dx. For the equation, so this is for the equation y prime plus p of x y equal to q of x. So the equation has to be in the normal form, right? So in this case, the ODE is not in the normal form. And so to adjust this, we're going to divide the ODE by 3. And if I divide by 3, then the equation becomes y prime plus 5y is equal to 2x. Well, so now this is in the normal form. And so p of x is equal to 5, so mu of x should be e to the power integral of 5 dx, which is e to the power 5x. And then we know that if we multiply the equation by the integrating factor, so multiply my ODE by mu, and I have to multiply the ODE, which is in the normal form, right? So we take this guy, we multiply by mu of x, and then we know that from the product rule, the left-hand side is going to look like mu of x times y quantity prime, and this is equal to mu of x times q of x. So in this case, mu is the exponential, q is, as we can see from here, 2x. So what we get is e to the 5x times y prime is equal to 2x times e to the x. And now if the derivative is of something is 2x e to the x, then that something must be an integral of 2x e to the x. So integrating e to the 5x times y prime, we recover e to the 5x times y, and that should be the integral of 2x e to the x dx. All right, now assuming that you reviewed integration techniques, you recognize that this integral has to be taken by using integration by parts. So we make u equal to 2x, right? That's the factor that we want to remove in this case by taking a derivative. So that du is 2dx and dv is e to the 5x dx, so that antiderivative of that, v is 1/5 e to the 5x. And so what we get is u times v, 2x times 1/5 e to the 5x, that is 2/5 x e to the 5x, minus integral of v du, so minus 1/5 integral of 2 e to the 5x, so 2, actually it's 2/5 e to the 5x dx. All right, and then antiderivative of e to the 5x is 1/5 e to the 5x, so we get 2/5 x e to the 5x minus 2 over 5 squared, 2/25 e to the 5x plus a constant. And so finally, then what we get is that if we solve for y, we need to divide by e to the 5x or multiply by e to the minus 5x, and y is 2/5 x minus 2/25 e to the 5x is gone, so just minus 2/25 plus c e to the minus 5x. And so the equation has been solved. Let me check one thing here. So let's verify the following property. So we have, in this case, a solution which consists of two parts. Now, one part is 2/5 x minus 2/25, which does not depend on the unknown constant c. And then another one is c e to the minus 5x. So what I want to try to do, I want to take these two pieces and separately substitute them into the left-hand side of my original equation, which is the equation here. And I want to see what happens to the left-hand side. So in total, I know that because this is a solution, if I take this expression and I take its derivative and I substitute everything to the equation must be satisfied because the equation is solved by this one parameter family of solutions or a general solution. So let's refer to it from now on, a general solution of my ODE. Because presumably it includes all possible solutions, or all possible particular solutions that you specify by choosing different c's. All right, so I'm going to consider two functions. I'm going to call one of them yp of x equal to 2/5 x minus 2/25. And I'm going to consider the second guy and yh of x to be c e to the minus 5x. All right, so then let's see, what is yp prime? That is going to be just 2/5, right? Because yp is a linear function. And if I take derivative of yh prime of x is minus 5c e to the minus 5x. All right, and so now I'm taking yp and substituting into my equation. So yp and yp prime. So the equation again is, the left-hand side looks like this. So I'm going to evaluate that at yp first. What should this give me? It should give me 3 times yp prime, which is 2/5, plus 15 times yp, which is 2/5 x, minus 2 25ths. And let's see how much that is. So this is 6/5. Now 15 times 2/5, 5 cancels out, right? So that would be 3 times 2, so plus 6x. And then minus 15 times 2, or 25. Again, 5 cancels out, so we have minus 6/5, right, if we distribute 15. All right, and so then it should not come as a big shock that 6/5 goes away, and this is equal to 6x. My original equation again is right here. So the right-hand side is 6x. So what we get from here, so hence yp is, now yp doesn't have any c's in it, no generic constants in it, so yp is a particular solution to the ODE. Non-homogeneous ODE. Recall, non-homogeneous means that the right-hand side is not equal to 0. Free y prime plus 15y equal to 6x. Okay, so then now let's do the same thing with yh. 3 times yh prime plus 15 yh, what is that? This is 3 times, here's our yh prime, minus 5 c e to the minus 5x, plus 15 times yh, so yh is c e to the minus 5x, so 15 times c e to the minus 5x. Well, and then you notice that if you distribute 3, then you get, if you multiply the expression in parentheses by 3, you get minus 15c e to the minus 5x. You're adding 15c e to the minus 5x, so everything cancels out, and you get 0. And so the conclusion here, yh solves a homogeneous equation with the same left-hand side as a regional ODE. All right, and the left-hand side of the original ODE was 3y prime plus 15y, but right now it is a homogeneous equation. So this is equal to 0. So then we conclude that the way the solution of our linear ODE looks like is this. And in fact, yh is not just any solution, but it is a general solution because it depends on an unknown constant, right? So there is one unknown constant. So in fact, YH is a general of this ODE. So we can make the following conjecture then. So that the solution, not just a solution, but a general solution, and again, I'm using the terminology general solution now for whatever many parameters I need to solve my ODE. So in this case, ODE is the ODE is of the first order. So the one parameter family of its solutions, which should encompass all possible solutions, would be enough. So there is one parameter here. It should be one parameter. So if I look for general solution of this non-homogeneous linear ODE of a non-homogeneous linear ODE is a sum of a particular solution of this ODE and a general solution of the corresponding homogeneous equation. So we're making this conjecture, and what I would encourage you to do is to try to verify this for the examples that we have done already. So what I mean in particular is this. If I go to the previous example that we did last time, right, the solution, general solution of a non-homogeneous ODE of this form has structure 1 plus c e to the minus x squared over 2. So it looks like something that does not contain c plus something which is a multiple of c. So then from our conjecture, we guess that 1 should be a solution, a particular solution of a non-homogeneous equation, and this should be a general solution of a corresponding homogeneous equation where you replace x by 0. So it will be actually very easy to check if 1 is a particular solution. If I take y equal to 1, then y prime is 0, so I'm multiplying x by 1 on the left, and I have x on the right, so indeed 1 is a particular solution. And then by taking a derivative, you can verify that this expression is a general solution of the same ODE, but with the right-hand side being equal to 0. It is important to realize it now because later on, when we're going to solve linear equations of higher orders, you will see that a very similar structure would persist there. And actually, this will provide us with a method of solution of linear equations of higher order. Okay, maybe one or two more examples. Yes, let's see. So, example. Let's try to solve the initial value problem. Let me see what I want to solve here. Okay, let's try let's try xy prime plus 1 plus xy equal to e to the minus x sine 2x. And let's say that y of pi is equal to 1. Okay, so we need to solve the equation and then use the initial condition to find the value of the unknown constant. So we need to find the general solution of the ODE first and then determine the unknown constant. Okay, so this is a linear equation, right? Because you have a function of x multiplying y prime, another function of x multiplying y, and a function of x on the right. So this would be a linear. The right-hand side is not zero, so non-homogeneous. Equation of the first order. So to solve it, I have to use the integrating factor. And then I can use the integrating factor once I wrote the equation in normal form. So the first step, rewrite the ODE in a normal form. If it was already in a normal form, then of course you don't need to do that. But in this case, it isn't. So that involves dividing everything by x to get y prime plus 1 plus x over x times y times 1 over x e to the minus x times sine of 2x. All right, so that's our ODE in the normal form. So then the integrating factor, mu of x, is e to the power integral of p of x, which is a function of x in front of y. So that is 1 plus x over x dx. Now, in this case, typically what you want to do is to evaluate the integral and simplify it as much as possible, because unless you do that, then the second integral that you'll have to compute is going to be either extremely complicated or just untakeable. So what is this? This is e to the power integral of 1 over x, if I divide by x, plus 1 dx. So that, if I integrate 1 over x, is natural log of x. If I integrate 1, that would be x. And because I need only one integrating factor, I don't need many, I don't add c when I'm doing this integration to find the integrating factor. Okay, so then the function e to the ln of x plus x looks nasty, right? Because at the end of the day, again, you'll have to be integrating this function times something else. So it makes sense to simplify it as much as possible. So if I have an exponential of the sum of two things, then that's the same thing as e to the power first thing times e to the power the second thing, right? That's the properties of exponential. And then e to the power log is x. So x times e to the x is my mu of x. All right, and so then I know that the rules for solving the first order linear homogeneous ODE while using the integrating factor is that if I multiply the left-hand side by the integrating factor, the left-hand side of my equation, right, so I take this equation, multiply by the integrating factor, so then the left-hand side will look like the integrating factor times y quantity prime. So this would be x e to the x y prime. Right, that's a reason to introduce an integrating factor because it's a function which will turn the left-hand side, once it's multiplied by the integrating factor, into integrating factor times the function, the whole thing prime. So there's a product rule that is involved. And this should be the same thing as the existing function on the right-hand side multiplied by the integrating factor, x e to the x. And now you see why I advocated simplifying mu of x as much as possible, because now you see that x here will cancel with 1 over x, and e to the minus x times e to the x, that is also 1, so those two will cancel. So this is nothing but sine of 2x, which is going to be very easy to integrate. So if I take now integral of both sides, integral of a derivative on the left is x e to the x times y, and this should be equal to the integral of the function on the right, sine of 2x dx. And then the integral of sine of 2x should be minus 1/2 cosine of 2x, again assuming that you reviewed integration, plus a constant. And so finally, then I can find y by dividing by x e to the x. So y should be equal to minus cosine of 2x divided by x e to the x plus c divided by x e to the x. All right, so this is my general solution, and per our discussion in the previous example, I do expect that this thing, which does not contain c, this is a particular solution of the non-homogeneous equation of my original ODE. And this, the part that contains C, is a general solution of the corresponding homogeneous ODE. Okay, and so now I'm going to use this to find this particular solution to my initial value problem. So the initial value problem required y of pi to be equal to 1. So let's insert pi into y. So I know that y of pi on one hand is equal to 1, but on the other hand it's going to be minus cosine of 2 pi divided by pi e to the pi plus c over pi e to the pi. Now, cosine of 2 pi is, of course, so this guy is 1. So what we have is that if we multiply everything by pi e to the pi, we have that pi e to the pi is equal to minus 1 plus c. So c is pi e to the pi plus 1. And so now that I have c, I can plug it back into my general solution of a non-homogeneous equation, and that will give me a particular solution of the initial value problem. So therefore, y is equal to minus cosine 2x over x e to the x plus c, which is pi e to the pi plus 1 divided by x e to the x. So this is a solution of my initial value problem. And so we're done. All right, so in the next lecture, I'm going to discuss another class of equations that we should be able to solve by using an appropriate method.